This interactive visualization will allow you to adjust the number of neighbors we use to choose to make a prediction for our model. The number of neighbors is a key hyperparameter to the k-nearest neighbors model. So generally speaking, how does our decision boundary change as we increase the number of neighbors? Generally speaking, as we increase the number of neighbors, the decision boundary gets smoothed out. We'll explore the consequence of that just in a bit, but that is happening when we change the number of neighbors. Now going back to the Minkowski distance, you can view that our k-nearest neighbor model has two key hyperparameters. It's the distance metric, how you're going to define distance, as well as the number of neighbors you should include for making predictions. But we don't have to use the Minkowski distance. Let's use a different distance metric. Let's talk about cosine similarity. Another way we can view our data points, we can view our data points as vectors in our p-dimensional space. So let's say here's the origin, and we have two observations. This observation there, and let's say this observation here. So we'll draw the vectors. This right here would be the Euclidean distance. However, what if we're not concerned about the length of these vectors? And we're more concerned about the general direction these vectors point towards. If that's the case, if we care more about the direction these vectors express rather than the magnitude, we can go and figure out how similar these two vectors are by measuring the cosine, the angle they form. This angle here, particularly the cosine of this angle. And the reason why we're looking at the cosine is let's consider a third vector that points in a very similar direction to this vector here with some deviation, but is rather long. So the distance, the Euclidean distance, is very large, but notice they point in a very similar direction, so they could be expressing a very similar idea. Then we notice the angle they form is very small. So if you take the cosine of the angle they form, that's going to be another measure of similarity with our data points. So we can use the cosine similarity instead of the Euclidean distance. So if our vectors are completely well aligned or completely aligned, point to the same direction, the angle to form is 0. In that case, cosine is 0 will be 1. And of course, if they are orthogonal to each other, something like this, they form a 90-degree angle, so the cosine of 90 degrees will be 0. Now regarding bias and variance, one of the things that we got to understand with these models is how does it affecting those hyperparameters, how will it affect bias and variance? One of the key hyperparameters are the number of neighbors. So if I increase the number of neighbors, am I going to increase variance or increase bias? As I increase the number of neighbors, will I tend to overfit or I tend to underfit? It's important to understand this behavior, get a feel for it, so we can better tune our model. So when answering these questions, one of the things that I like to do to help me best answer these questions is let's consider extreme situations. Let's consider the very extreme, where we have a model. It doesn't matter if we're doing regression or classification. Well, let's go ahead and say we're doing regression. We can talk about it, how it works for classification, if it's going to work very similar, but let's think about it in the eyes of regression. We decide to only use one neighbor, only use one training point in our analysis, only one training point to make a prediction. using that one training point, will that be a model with high variance or high bias? Will it be overfitted or underfitted? Let's delve deeper into the idea of variance. What are the characteristics of a model that has high variance? What are those characteristics? A model that has high variance will be overfitted. Another characteristics of a model with high variance is, let's talk about where its name is derived. If a model has high variance, that means the model is too dependent on the training data. It's starting to pick up the idiosyncrasies of our training data. No longer picking up the noise, the signal, but also picking up the noise. So if the model is too dependent on the training data, how would the model parameters or how would the model's performance vary if you give it a different training set? Yes, if you give your model, if you retrain the model with a different training set, you'd expect the model's performance, the model's parameters to change a bit. But if they change very drastically, if they're highly variable, that means we have a high variance model. So what could happen is, let's say we have a training set. I'll draw it out here. So this is my points here. This is one training set. And then I want to predict on this observation right here. So its nearest neighbor, its only closest neighbor, since I have set number of neighbors 1, is, let's say, this point there. So it just uses that one point to make a prediction. But let's say I'm going to wipe out my training data, so use a new training set. Add my new points. If that's the case, then the new nearest neighbor is this point. So since this other neighbor here, because we no longer have this point, because the first point belongs to the first training set, we have a new training set. Now it's highly variable. Notice the result is going to be very different. So the model's performance is going to be highly variable. So we have, if we're only using a very small number of neighbors, the model is going to be a high variance model. So given that, then it makes sense that if we increase the number of neighbors, eventually we'll move from a regime of high variance to high bias. But let's also answer this question on the other end. Let's not just assume, okay, one end is high variance, the other end should be high bias. Well, perhaps there's a lull, perhaps that's not the case. So let's go and answer the question coming from the other end, the other extreme situation. Let's consider the other extreme, where we're going to choose the number of neighbors we have in our model to make predictions is the entire training set. So I'm going to use the entire training set to make a prediction. In that case, can you characterize the model? Can you describe what the model is doing if it's using the entire training set to make a prediction and we're working with a regression problem? So we're using the regression version of k nearest neighbors using the entire training set. What value would it always predict? It will always predict the same value, right? Since we're using the entire training set, we're going to predict one value. We're always going to predict the mean of the entire training set. What does that resemble? What does that model resemble to you? We've played around with that model. We've seen that model. We use that model as a baseline of comparison. A model that always predicts the mean value of the training set. That's that mean regressor that we talked about. That's that baseline model that we use to construct the R-squared metric. If your model does just as well as predicting the mean as an R-squared value of 0. The mean regressor, that's a very simple, naive model. Is it going to perform very well? It doesn't matter what are the features, what are the characteristics of the observation. It's always going to predict that same value. It's a very simple, biased model. So we see on the other end, we've justified it to ourselves. And on the other end, as we use all our training points as neighbors, We have a very simple model, always predicts the same value, will predict the mean for regression, and that's a high bias model. So of course, somewhere in between is a good set of neighbors to use for our analysis. And we got to find those out. Now going back to, we answered this question with regression. We could have answered it using classification. Let's consider the case where we use our entire training set to make a classification. What type of model do we have there? Always predicts the same value. It will always predict, in this case, the majority class. So we have a very biased, very simple model on the other hand, as well when we look at classification. All right, so let's go play around with tuning our model. So we're going to do grid search, do a train test split. We're going to go ahead and tune our neighbors. Since we're using a pipeline, we call this step CLF to stand for classifier. So this is our hyperparameter we are tuning, the n neighbors hyperparameter for our classifier step. We're going to search through a range of, let's say, 1 to 35, steps of 35. Let's go ahead and tune the model. Okay, let's see what our cross-validation results were. Let's plot it out. So this indicates that as I increase the number of neighbors, my accuracy gets better, but at a certain point, my accuracy starts to drop. So we see this idea of underfitting, overfitting played out when we inspect the cross-validation error. And you can get those cross-validation results via this attribute from our grid search called CV results. It's a dictionary with different outcomes, different analysis, different statistics, applying the grid search cross-validation scheme when we fit that grid search object. When you're tuning your k-nearest neighbors, one of the things you want to ask yourself is, what was that best number of neighbors? And you also got to consider the range you're using. If for some reason we figured out that the best number of neighbors to use in this analysis was 35, then that means that, you know what, perhaps we didn't have a good grid. We didn't construct a good grid when we did the hyperparameter tuning. So in other words, and this is applicable to other models as well. Let's say this is the number of neighbors. Let's say this is, accuracy in this case, or some metric of interest. And it goes like this. So this tells me the best answer was here, the largest value we investigated. So that means that perhaps we need to extend the range we look at. Go into explore higher number of neighbors. So we can go ahead and repeat the grid search, but maybe go ahead and use a different range. Instead of this value to this value, perhaps we should consider this value all the way to this value. Because what might happen is it might further increase before plateauing. So sometimes it's nice that you inspect the best values and you make sure that they're not in the peripheries of the grid that you constructed when you did your grid search CV. And that's applicable to other cases as well. Let's say you're tuning alpha for your, let's say, logistic regression or linear regression, and the best alpha was near the periphery of that grid. Expand the grid, shift the grid, so you can observe perhaps a plateau occurring, so you can be more certain the best value overall.